Okay, my name is Bei Wang. I'm working as a software engineer in the Irish program. And in this presentation, I will talk about our recent work in preparing the parallel common filter tracking project, MKFit, for the same as high-level trigger during round 3. In particular, I will talk about how we actually start from the CMS raw script detector data and output the head information using GPU. And I will first start with the motivation, and then I will talk about how we actually choose the data structure and how we handle the three switch code algorithm parallelly on both CPU and GPU. And in order to increase the throughput, we want to enable multiple events processing the same time by both the CPU and GPU. And so I will present the performance result, including the throughput at the end. First, the motivation. We know that the reconstruction time increase exponentially at increasing pile up. Among all the tasks in reconstruction, tracking is the most time-consuming part. At the same time, as our computer industry is moving into modern architecture with wider vector units, where more cores on CPU and even many cores on GPU, it's important that we revisit our legacy code and also algorithm so that we make sure that the computing power from the latest hardware can be fully leveraged. And to this end, actually, there's like two major efforts with respect to code modernization in CMS. One is the PetaCrack project and trying to do the pixel tracking on GPU, and another is the MKFit, the parallel common filter project. And for this talk, I will mainly talk about how we prepare MKFit for the high-level trigger. And MKFit project was established in 2014, about 6 years right now. And over the last 6 years, we have made pretty significant progress in developing a highly parallelized and vectorized version of this code for tracking. And the previous work mainly focused on the CPU-based offline tracking. And to prepare MKFit for round 3, and particularly at the high-level trigger, we recently start to looking at the GPU-based tracking. And in order to avoid the overhead of moving data around, which is pretty expensive, we start our investigation doing the tracking chain from the raw silicon script data. And this presentation will talk about how we start from the raw data and how the raw data is being decoded and then formed into a cluster on GPU. And before talking about the implementation, I'll talk about how the raw data are organized from CMS silicon script tracker. And so in CMS, the basic unit of the silicon script tracker, where we call that SST, is made up of a front and driver or feed. And each of the feed has 96 optical channels, and each of the channels will have 256 scripts. And how the ADC or the charge value is stored in each of the channels in the SST. Here that the value is stored kind of in a way like how we store the sparse matrices in a compressed sparse row format. And overall, we have 440 feeds, and because each feed has 96 optical channel, and we have 256 scripts per channel, and overall we have about 10 million scripts. And in CMS, we only record the active scripts, which means the lowest level is above some switch code. And so we only have about, for example, for PU50 events, about like 500,000 scripts recorded for each event. And thus, this SST data is kind of stored event by event. And besides the SST data, in order to do the clustering, we also need the premier data calibration data, which include the information about if the script is good or bad, the gain value, and also the lowest value of the script. And those information is basically tracker based. So we only need to take one copy of those data for the later stage of clustering. And the unpacking part was mainly doing the data transfer, because structured array data format is more favorable for the modern CPU with wider vector length, and also better for GPU with coalesced memory access. So we choose to convert the raw data and also including the calibration data into the structure of array format. And we provide, once those data or the data are available as structure of array format, and we provide it as the input for the clustering. And the same as clustering is based on the three-threshold algorithm, and our parallel implementation is actually based on the fact that in this algorithm, there's one criteria that at least one of the state, one of the script needs to have single to lowest level larger than state script. And so based on this fact, we first kind of parallel scan all the scripts and find out where make a mask for the state candidate scripts, and this can be done parallelly over all the scripts. And after that, we kind of remove the labeling code state candidacy, because those scripts could end up with the same cluster, and we need to remove the duplication. And once we have the list of the state candidates, we can start parallelly looking at each of them and looking at their left and right boundary for potential clustering. At the end, that we check each of the potential clustering to see that if it's single to lowest level above the clustering threshold, and to be a kind of true cluster where it's a fixed cluster. And well, those steps can be done parallelly, and so works good on both like multi-core CPU and GPU. And at the same time, in order to improve the overall throughput, we develop a multi-events version where multiple events can be handled by CPU or GPU simultaneously. And on GPU, this is done by the GPU CUDA streams, and we have each core launch each core launch one stream, and the multiple cores will launch multiple streams and to handle multiple events at the same time. On one side, this strategy can help us to reduce the memory transfer overhead, because we can actually overlap communication and computation. And at the same time, this can also help us to maximize the GPU utilization, because multiple kernels from different streams can be running concurrently on the same GPU device. And we try to use the petatrack GPU infrastructure, for example, the caching memory allocator, to reduce the memory malloc and the log overhead. And on the CPU, this is done by using two levels of parallel for loops, listed parallelization using OpenMP. And on the outer level, we have different core where series handle different events. And inside of each of the events, we have multiple cores to handle that single event. And we also enable vectorization with OpenMP SIMD clause in the inner loop. For this nested parallelization setup, it's pretty important that we have the core, the shreds affiliation to the cores on the CPU, so the best performance can be achieved with the proper setup. And we measure the performance by actually kind of using the single PU70 event data to mimic the behavior of running about 840 total events at the same time. And how we do this is we kind of like do that in a listed loops. And in the inner loop, we have multiple events happen at the same time. And then on the outer loop, we have an iteration, basically doing this kind of concurrency iteratively one after another. And we can play with different combinations. But overall, for each of the cases, we make sure that the total events is 840. And for example, we tested that on our cluster, GPU cluster in Princeton, which equipped it with two board wheel socket as the host and one P100 GPU as the accelerator. And for the CPU simulation, we utilize workhorse, for example. The combination of 214 means we have two events running concurrently, and for each event we have like 40 cores to handle the scripts in that event. And we measure play with different combinations and measure the throughput from both the CPU and GPU. We found that the GPU actually give us pretty nice throughput, and it's about like 20% better than the whole CPU throughput. And we are pretty actually encouraged by the current throughput result. And so this is a summary page, and we have developed a parallel and also vectorized version of the unpacking and clustering algorithm. This works pretty right now good on both multi-core CPU and the GPU. And our plan next is to integrate this piece of standard on our work into the same MSSW framework. We should expect very few changes to the kernels and to be part of the framework. And but at the same time, we need to make sure that we produce the identical result as the original MSSW algorithm. Besides that, we're also going to work on the head producer, which actually transforms the cluster into the global head coordinates, because that provides the input for our track build for the MK-fit. And while we investigate the GPU as the accelerator, we were also starting looking at the FPGA and as a counterpart for the GPU. And this is mainly using the OpenCL implementation. And that's for the talk, and thank you very much.
Great, thanks, Bei. There's time for one or maybe two questions. I lost my list of people, sorry. Seems there's none, so thanks again, Bei.